Joan Bruna. Joan Bruna is currently Associate Professor at the Courant Institute of Mathematical Sciences of New York University. He belongs to the Department of Computer Science, the Department of Mathematics, and the Center for Data Science. He is a leading member of the group on computational intelligence, learning, vision, and robotics, the CILVR, founded by LeCun, and also belongs to the Math and Data Group. Joan Bruna has degrees in mathematics and telecommunications engineering from the Polytechnic University of Catalonia, a Master of Science in Applied Mathematics from the École Normale Supérieure of Cachan, and a PhD 2013 from the École Polytechnique in France, in Paris, supervised by Stéphane Malat. He has been assistant professor of statistics at the University of California at Berkeley and was part of the Berkeley Artificial Intelligence Research Initiative. At present, he is the advisor of 11 PhD students and supervisor of 2 postdocs. He has engineering experience in the private sector and is the author of, or co-author of 7 patents. Some other honors. In 2018, he was awarded a Sloan Research Fellowship. In 2019, he received the National Science Foundation Career Award. In the period fall 2019, spring 2020, he was a member of the School of Mathematics of the Institute for Advanced Study in Princeton, New Jersey, coinciding with the year on optimization and machine learning. Since 2020, he is a visiting scholar in the Center for Computational Mathematics of the La Flatiron Institute of the Simons Foundation in New York. And in 2020, he received the Outstanding Paper Award of the International Astrostatistics Association. The title of his lecture is, you are seeing it in the screen, but let me read it. We are ready to listen to your lecture with this title. Thank you, Joan.
Thank you very much, Sebastián. Welcome, everyone. Thanks first for the invitation, and sorry that I'm not going to be able to be here. It's always a pleasure to be introduced by a former professor. So thank you, Sebastián. That was very, very touching. Okay, so I'm going to be talking today about some of the role of mathematics that can have in the modern understanding and the modern world in which we need to learn more and more from data coming from the physical world. So I guess the reason why we are all here, the reason why we are all here is because I guess in the last 10 years, we have seen really like an experimental revolution brought by machine learning techniques, in particular by deep learning techniques. It started in computer vision by solving problems in classification, also several problems in segmentation. But then more and more, we are seeing that this is a trend that is really going to essentially eat and span all areas of computational science, right? From biology to chemistry to physics, et cetera, et cetera, et cetera. And so as mathematicians, when we try to set up the problem and try to understand what's going on, we are left with, we see that these methods are essentially a conglomerate of very simple ideas. So what we see, the first thing that we can realize is that, yeah, these methods are able to really extract very complicated information from very high dimensional data, right? All these signals that you see here live in very high dimensional space. And the way they do that is by essentially learning what we call representation learning. So instead of relying on handcrafted features that maybe scientists have spent years thinking of, they let the algorithm choose the features from themselves. And the learning algorithm is actually something relatively naive from the perspective of optimization and statistics, which is just like first order methods. So this all seems very nice, but we're in a situation where right now, the technology right now is not completely satisfactory, in particular from the perspective of a mathematician trying to understand foundations, right? These methods, they're insatiable and they are inscrutable, right? In the sense that it's very hard to understand what's going on. So what I mean in terms of insatiability is that if one looks at the current trends, these methods, deep learning architectures in the modern world, they require more and more and more computational power. They require data sets that are bigger and bigger. And of course, they involve models that have very large number of parameters, right? So this means that training and developing and deploying these methods is just a matter of only very few key players like Google, etc. And so that's really like something that you cannot afford in many areas in science where this technology could be useful. There's another problem that as a theoretician you might feel is that right now, these, this deep learning area, this might look like a zoo, from, before geology started to actually make sense of all the species, right? Every model seems like a completely different beast. And so what is the thing that is bringing all these things together? Is there some kind of fundamental set of ideas that make all these models, something a little bit, something that one can make sense in a bit more like a principled manner? And so I guess that the overarching question of today that I wanted to communicate is, can we actually work towards a mathematical framework that can help us to bring these kind of guiding principles, understand what are the key questions that are still unanswered, what are the questions that I think we have a good idea on how to approach, and how can we leverage this mathematical framework, this mathematical thinking about the problem. And so I'm gonna hopefully, if I have enough time, to basically do like a little tour of this question in 3 different episodes, right? The first, we are going to describe some mathematical models for how to learn in high dimensions when data comes from the physical world. Then we are going to spend some time talking about some class of models that we call this geometric deep learning. And then we are going to see, if there's time, a couple of applications that I think highlight what is the role and the usefulness of this mathematical thinking about the problem. And so for those maybe people in the audience who are not familiar with what machine learning is about, here's a one slide summary. Supervised machine learning is really the problem of estimating a function in high dimensions, right? So we want to estimate a function that is defined over data that is in a very, very high dimensional space. So to formalize this question, we need to introduce like a few very important key concepts. The first one is that the way we measure errors and the way we train the model is relative to some data distribution, right? So this data distribution is the thing that defines a metric, right? As you can see here. And it's the source of all essentially physical structure that will come later in the talk. The way we are going to fit models, like estimate this function that is unknown, we are going to estimate it with some class, an approximation class. And many in most of the applications I'm going to talking about today, this function class is parameterized by, for example, a neural network. Okay. And then we are going to evaluate this function class using some measure of error. For example, as I said before, it's the average error with respect to the data distribution. And because this quantity of error, this measure of error, is unknown to us because we don't have access to the whole data distribution, we only have access to a few measurements, right? We need to estimate this function by observing only the value of this function in a few data points. So we are going to rely on these two functions, right? So we are going to train on the empirical version of the loss, but evaluate on the population loss. Okay, and the algorithm, like the classical algorithmic framework to do that, is what we call this empirical risk minimization. Okay, so I'm just going to describe it without going too much into the details. This is a method, is an estimation, it produces an estimator, f hat, that is good at minimizing. It has a small empirical loss. And it has a small empirical loss with a complexity, with a hypothesis that doesn't have huge number, right? That is a hypothesis that has small complexity. All right, and so the understanding when a machine learning algorithm is going to do well means that it's going to perform well on the data that we have not seen before, right? That's what this quantity tells us. So understanding when this function will do good is equivalent, amounts to understanding different sources of error, right? And to go to not to spend too much time here, I think the key thing to take home is that this error can be decomposed into three different, like the nature of the error has completely three different nature, right? Three different flavors. The first one is like an approximation nature, which is really about how can we construct approximation spaces that are adapted to the functions we care about. In other words, where this approximation error is going to be small for functions that have small norm, right? So we want to build norms, if you want, or like a hypothesis spaces where the norm, like small norm, means that the function is likely to happen. Then there's another source of error that is what we call the statistical error. That is the price we pay when we use a hypothesis space that is too large, right? Because we are optimizing the wrong function. We are optimizing the empirical version of the loss rather than the population version of the loss. And finally, at least the last term, but not by no means the simplest one, is the computation, like the optimization error that measures our ability to solve, to minimize these objective functions, right? So these problems. And these problems are optimization problems in very high dimensions. Okay, so typically there will always be some error in solving this empirical risk minimization. So the goal of the game is how can we build mathematics that are able to control at the same time these three sources of error, especially when we think about problems in high dimensions, such as the ones that you saw in the first slide. And so the way we make progress in machine learning, and in particular in deep learning, is to start by describing spaces of functions, right? The hypothesis spaces that are generated by simple neural network architectures. And the simplest neural network architecture is one that has only one hidden layer, right? This is what we call a single hidden layer neural network or a shallow neural network. So this architecture is going to define a function f, and this function f, you can think it as a sum, as a linear combination of very simple functions, right? This is what we call in analysis a ridge function, ridge, right? Because it's a function that only sees variation in one direction, right? In direction that is where I project the data. So I can play with the direction in which I project the data, and then I can stack a bunch of these functions to construct my hypothesis. So this is a model that is not unfamiliar, right? The analysis in people who are studying harmonic analysis and function analysis are quite familiar with this model. Why? Because in fact, these are class of architectures for which we can easily understand their approximation power, right? So we know that, for example, these are architectures when the number of units grows, right? So when the number of neurons, when the size of the width of this layer grows, we can approximate any continuous function in the relevant topology. But of course, this is not very quantitative at this point, right? This is just saying that if we have a sufficiently large architecture, we can approximate any function. That's not very surprising. Why this is not very surprising? Well, you can actually think what would happen if you pick as an activation function the complex exponential, just to get a grasp of what's going on. What the previous result is saying is essentially that the inverse Fourier transform, right, is dense. I can approximate any function that is continuous by a linear combination of Fourier atoms, right? This is a kind of a very classic and fundamental elementary result in harmonic analysis, right? We know that the truncated Fourier expansion converges to the function if I have enough regularity, right? In that case, if the function is continuous. What is actually bad news is that the rate in which this truncated expansion converges to the function is cursed. It's cursed by dimension, right? So what it means is that if I want to make this approximation, if I want my neural network to approximate my function with certain error epsilon, the number of units I need, n, needs to grow essentially exponentially large in the error. Unless the number of derivatives that I impose, right? So unless my hypothesis, right, the function that I will need to learn is assumed to be very, very, very smooth. Like in the picture I try to plot here in the right, is that think about the function that is defined in a very high dimensional space. If I want to approximate this function with a small number of Fourier atoms, the only way it's going to work well is when this function is extremely smooth, right? Where all the energy is concentrated in the low frequencies. That's not very useful. So these researchers, of course, they were very, very, very much aware of this problem already in the 90s. People who were studying neural networks 30 years ago. And so they realized that maybe one could turn the question on the upside down, right? So instead of looking at very classical spaces of approximation like the Sobolev class and studying approximation rates with neural networks, maybe we can do the opposite. We can look at what is the space of functions that is kind of adapted to approximate well, right? That is adapted to the shallow neural network approximation. And this is the pioneering work by Andrew BARRON in the 90s. We basically introduced this class of functions, which if people here are a little bit familiar, they will identify that this is really bringing us to a different world, right? This is the world of sparsity. This is the world of L1 representations, right? So here, if the function is sparse in the right sense, in the sense that its Fourier transform is integrable, not square integrable, then I can break the curse of dimensionality and have approximation rates that are not cursed by dimension, right? But this is really assuming that this is so the question is, how strong is this assumption, right? So how strong is this assumption in the physics for functions that are defined in the physical world? Are we done? Well, you might anticipate that we are not probably done, because otherwise, I mean, that was something that happened 30 years ago. And so let's try to motivate why this hypothesis might be a bit too strong for us. And let me just try to motivate it by trying to approximate this function f of x that maps any input image to whether there's a crab or not in the image, right? That's, of course, a very simple illustration. And so essentially, functions that are in BARRON that have this L1 norm in the Fourier transform that is finite essentially mean that I would be able to approximate very well this function by basically a linear combination of local functions, right? So if I think in terms of this diagram here, you would think that whether there's a crop or not in the image, I can infer it by basically stacking up information that is local, right? So I aggregate information across the patches. And this is really disregarding all the interactions that you have between patches, right? The information that I'm looking for is not something that I can extract as a separable sum of local things that I can extract, right? In general, I need to be able to account for all the ways pixels interact with each other, even though they're very far in the grid. So somehow, the key to break the curse of dimensionality is that when we look at this image, we are staring at a low dimensional structure, right? But this low dimensional structure, it's in the domain in which this signal is defined, right? Like instead of thinking that the input is a point in a very high dimensional space, the input is actually a signal on a two-dimensional grid. So this is where we basically need to extract. This is maybe where we need to play our advantage. And so that is what brings us to this notion of geometric function classes. Okay, so we are going to postulate and we are going to exploit the prior knowledge that we have. Is that the function is defined again in a very high dimensional space, but this input domain X is in fact a space of signals that are defined over a low dimensional grid. And what are the structures that we can assume known from this class? So the kind of transformations that we assume that the function is regular are transformations that are kind of naturally defined in the low dimensional grid, right? And here I'm plotting you a famous video by Philip Scott Johnson of how you can actually smoothly transition from 500 years of different art in female portraits. As you can see, these transformations, they are not something that you can model well by assuming that the function is Lipschitz or the function is Sobolev or the function is BARRON, right? So here you are really exploiting the fact that these are diffeomorphisms defined over two-dimensional grid. And so we really need to exploit this kind of regularity, like these regularity assumptions, in order to actually make progress in this problem. All right, so the question is really how can we leverage this prior and use it to our advantage? So this is what brings us to the second point. This is the notion of geometric deep learning. All right, so the first natural idea of I think maybe the answer, like the first response by anyone that has been thinking about this problem is to say, well, yeah, very nice. There are some transformations on the input where the function I need to approximate doesn't change. And this is like the symmetry of the problem, like the invariance with certain transformations that I can make to the input that do not change the output. For example, here in this little diagram, I'm plotting the effect of rotating the input, right? If I rotate the image, maybe the identity of the painting doesn't change. And so, as you know, the symmetries have a very rich algebraic structure. They form a group by composition. And so it's very natural to say, well, if I have a target function f star, right? And you tell me that this target function f star is invariant, maybe I can take any hypothesis space F, arbitrary, and just restrict my learning into only those hypotheses that satisfy these invariants, right? So I'm just looking at only the subset of F, capital F, that satisfy this invariant assumption. Of course, this is a no-brainer, right? Because I'm learning over a space of hypotheses that is smaller, and I'm not reducing my approximation error. Just because the target, I'm promising you that the target is in that little green subspace, right? So everyone would prefer to learn on the green hypothesis than in the blue hypothesis. That's not the question. The question is it this sufficient, right? Can you quantitatively show improvements by using these invariants, leveraging these invariants? And so just to give you kind of the punchline here, and this is a work that is presented this year at NeurIPS that is done with my postdoc Alberto Pieti and a PhD student Luca Venturi. And so let's focus on just the class of like the Sobolev class or like the Lipschitz class, just to bring these ideas home. Right, so the initial hypothesis of if you just assume that the function is smooth, like it's Lipschitz, for example, this is the Lipschitz property, right? It means that if I move in my ambient space, like the difference between the two, like the value of the function at 2 points is proportional to upper bounded by the Euclidean distance between the 2 points. Now, when I introduce invariants, I'm replacing this kind of pairwise distance between images to pairwise distance between the orbits, right? This is what's called the ensemble, like the manifold of all the possible transformations of the image, right? So because this metric is much weaker, this is actually a semi-norm, is much weaker than the original norm. The hypothesis, right, the saying that my function is invariant, it satisfies this, it's Lipschitz with respect to the semi-norm, it's a much stronger hypothesis, right? In particular, it implies that my function is invariant. So you might wonder, okay, now I have a hypothesis of a function that is much stronger. Does it mean that I can learn with less number of training points? So the first answer is yes, right? And this is captured by this result that I state here informally, is that if I use a learning hypothesis, in that case, it's the right way to exploit this regularity is to use a kernel, right? And so if I use a kernel that is invariant to the group action, then indeed I can improve my ensemble complexity, right? So I can certify that the function, my estimator, is going to have an error in the population sense that is much smaller than the error I had before, and the gains are basically of the order of the size of the group. Okay, so if the group of transsymmetries is very large, I'm gonna have more gains than if the group is very small. But you can see that there's still a problem, right? And if you stare at this equation for 10 seconds, you will see there's a problem. Because even if that group was very large, say exponential in dimension, this is still like inside an exponent that is scarce by dimension. Okay, so even if this was like, let's say, proportional to d, like alpha to the d, this would be killed by this exponent, right? So at the end, it can only explain gains that are constant, right? So that we only gain like a constant factor in generalization. So in other words, the curse of dimensionality is still cursed, right? So we are still cursed. This model is not sufficient in itself to break the curse of dimensionality. Let me just say that these results are, this is not just like a statement about the upper bounds. These are tagged, right? So we have minimax lower bounds with a matching constant, right? So there's gains that are real, but they're not sufficient. All right. And just to give you a little bit of what is behind this result, this is really about like the tools that are needed to prove this kind of results are basically just understanding well invariant harmonic polynomials. Right? So here we use harmonic analysis on the unit sphere, and it's all about trying to understand very well counting how many polynomials at every degree are invariant with a certain group, right? And this is something that we build upon some of the nice work by Andrea Montanari, Song Mei, and Theodor Mikiasevich. All right, so the takeaway really is that we need to complement this prior with something else, right? We cannot just rely on invariants. And so you might say, yeah, of course. I mean, if you have watched a few talks by kind of the pioneers in the field, for example, Jan LeCun or Yoshua Bengio, they, of course, have been pretty much aware that the thing that might be responsible, or one of the key properties of the deep learning is so useful is there's this notion that they call compositionality, right? Like the bypassing the course of dimensionality relies on some amount of compositionality, right? That instead of learning my complicated function in one step, I break the learning problem into different steps, right? Of course, this is very informal, right? I mean, the question is really, what does this thing mathematically mean, right? So how can we formalize this notion mathematically? And so one key tool to maybe make progress is really to rely, like to connect it with a very classical notion that has been, in a sense, like a foundational notion in the study of many physical phenomena. That is this notion of multiscale, right? And I like to motivate it by this example. It might be very simplistic, right? But if we want to understand life as a whole, right, like anything that lives, of course, we can start by looking at quantum mechanics, right? We can start by looking at Schrodinger equation just to understand how atoms move. But then, with this, following this program, it's going to be very hard to understand how a human body works, right? So we need to basically break the problem into different stages, different scales. And this is a phenomenon that appears in many areas, right? Not just in this example, but want to study like how fluids operate, phenomena of percolation, etc. There's always there has been like an important benefit to try to understand the phenomena at different scales, right? To explore the multi-scale structure of the problem. And so here we are lucky because we are dealing with a problem, in particular focusing in grids, where we have a very rich toolkit to exploit the multi-scale structure. And this is something that was the beginning of my journey in this problem, because that's the kind of the work that I did during my PhD together with Stefan. And so in the grid, let's see how we can connect multi-scale structure with a problem with a wish list with the invariance priors that we had before. So we can start by looking at like in the grid, the relevant group is the translation, right? So we need the invariance of translations. So we can start by looking at the problem in the linear sense, right? So we can start by trying to describe operators that are linear and translation invariant. May I ask that people mute themselves, because I see that there's someone who hasn't muted. I'm hearing some background noise. Okay, thank you. So these are like the only operator that is linear and is invariant to translations is the average, right? And if you think about the local version, it's just a blurring, right? So that's an operator that's very simple to describe. And this operator is, in fact, not just translation invariant, but in fact stable to things that are nearly translations, right? Of course, with this operator, we are not going to go very far, right? It's an operator that just throws all the high frequency information. And so the question is really is how can we complement this operator, right, with an operator that is going to recover the information that is lost by this low pass. And so it turns out that instead of looking at linear invariance, we can look at linear equivariance instead. Okay, so these are operators that are linear and commute with the action of the grid, right? So you can actually verify that in the grid, like any linear operator that commutes with translation is a convolution operator. And among these operators, we can focus on those that again satisfy this stability to deformations, right? Like what I described before, that the kind of transformations that we know exist in the physical world are not just translations, but things that look like the action of the form of physics. So amongst all these convolutional operators, which one are those that are stable to deformations? So it turns out that again here the multi-scale structure is the thing that really saves the day. Because if I look at the family of convolutional operators that are constructed by a family of multi-scale wavelet decompositions, right? So basically think about a filter bank where I have a bunch of filters and every filter is localizing the information at a certain scale, right? So if I consider this filter bank, then I'm complementing the information that is lost by this low pass filter, and I'm doing it in a way that is stable to deformation, right? So it's like nearly commuting to the action of deformations. And so now we have these two main ingredients that are linear transformations, and we can start to combine them together by introducing a nonlinear activation function in between. Right? This is the key step that allows us to combine several of these stages together. And so I'm just going to try to describe very briefly how it works. This is what's defined what we call the scattering representation. Okay, so it's a representation that is just built by this first principle by trying to assemble the three blocks that I described before. So the first block the first features that I can extract are just applying my stable linear operator, which is the low-pass filter. And then the information that is lost by this low-pass filter, I can recover it by one stage of wavelet filters that I pass through my nonlinearity, and then I can filter them again. And every time I apply a low-pass filter, I lose information. This information, I can recover it in the next stage by never more wavelet coefficients, right? By repeating this operation. So if I keep doing this again and again and again, I end up with a representation that is just obtained by assembling all these coefficients. And because this representation is obtained by composing only these three operators like W, rho, and A, and each of these three operators is stable, then by composing stable operators, I preserve the stability. All right. So this is a representation that is something that you can use to classify, to solve simple classification problems in images, for example, handwritten digital recognitions, textures, etc. Of course, for those of you who might be familiar, this is familiar, this looks a little bit like a convolutional neural network. It's not quite there because here we are using wavelets instead of arbitrary filters, and because you are using this kind of tree representation, right? So every time I decompose the image into a subband, then I'm not going to recombine the wavelet subbands together with each other. So in other words, there are no interactions between channels. Of course, this makes the analysis very simple, but it impacts the approximation power. And so the GNNs are kind of the natural extension, and this is an architecture, for those of you who are not familiar, that was developed in the 50s and the 60s it has its roots in the neuroscience community, but was really brought to kind of the engineering glory by Jan LeCun in the 80s and the 90s. And so this is really a representation that instead of relying on these like handcrafted wavelet filter banks, it just considers like a family of local convolutional operators, right? So I'm just going to consider a family of operators that think about them as kind of partial derivatives, right? I'm just going to extract local edge detectors into different angles. And that's kind of my dictionary of operators. And now what every layer is going to do of the transform is going to learn kind of a polynomial on these operators, right? It's going to learn a linear combination of these stable operators. And every time, and once I have this linear combination, I pass to the next layer by applying this pointwise, element-wise nonlinearity, right? Just because, of course, this pointwise nonlinearity is what allows me to basically create more and more different features, right? It's gonna improve my approximation power. And so the takeaway here is the same thing, right? Is that if I understand very well the linear equivariance structure of the group, right? And I use local linear equivariance, then I can basically start playing with them, right? I can create this, it's almost like the key point in the Lego, right? So once I have this building block, then I can start cranking like applying it again and again and again and create very rich structure. Okay, so the question is really how general is this procedure? How general is this way of thinking about the problem, right? That I can, if I understand very well the linear equivariance structure, then I can construct very rich representations. And so when I say more general, I'm thinking about problems that involve not just the grid and solving problems in image classification, but maybe problems that involve, let's say, chemical data, right? And chemical data, I can model the input as a graph. Maybe every node on the graph is an atom, and every edge is kind of a bond. Or maybe I have data that is naturally modeled as some kind of manifold, like a Riemannian manifold. For example, if I'm trying to understand some problem in computer graphics. So here we have domains that are, obviously, they all encode some kind of metric, like geometry on the input. And so I can encode these domains, I can use these domains, I can embed them and feed it into my computer, into my algorithm. In the case of a graph, for example, I can embed them through their adjacency matrix. And so this embedding induces like inherent symmetries on the problem. For example, there's multiple ways I can encode a given graph with an adjacency matrix, right? If I have two adjacency matrices that are conjugate to each other, meaning that I can find a permutation in the rows and the columns, then there's the same object. And the same way for a manifold, for a remaining manifold, I can encode them up to diffeomorphism, right? It's the same geometric object. And so here we really have the problem again, that not only we have the symmetries that are very rigid, but we also have like an inner notion of closeness, right? Like the same way that we had these diffeomorphisms, these paintings that were close to each other by a small diffeomorphism. Here we have the same thing, right? We can think about two molecules as inherently close to each other, depending on, for example, of how this deformation is measured. Okay, like there's an intrinsic notion of distance between these objects. And so can we apply the same paradigm, namely, if we understand very well the linear equivariant structure, can we use it to define a rich class of architectures? Okay, that is going to naturally be stable to this family of deformations. So it turns out that, again, using by no means new mathematics, like these are mathematics from, I believe in the even the 19th century, we can do so, right? So there's a notion that is very intrinsic, right? That one can apply in very, very general geometries of a low-pass filter. And this is just a notion of a diffusion, right? It's like some process that is going to propagate information, right, by some kind of local average. So I can define a diffusion operator on a graph. I can define a diffusion operator on a manifold. And then once I have a diffusion operator, I can also define the notion of like a high-pass filter, right? Because I can just look at, the difference between diffusion at different time steps, right? I have a difference of low-pass filters. I have a natural high-pass filter, right? And this is, again, something that is quite fundamental in many areas of geometry, which is the Laplacian, right? So I can define the Laplacian operator on a graph. I can define the Laplace-Beltrami operator on a manifold. So I have here my dictionary. I have a dictionary of how to compute the low-pass filter, and I have to compute the high-pass filter. And so once I have this dictionary, right, I can define again a family, my dictionary of operators, that they are intrinsic. So it means that they are completely equivariant to the way I parameterize the domain, right? So if I change the permutation of my nodes, the operator is going to be aware of that, right? It's going to take this. It's going to take this for me. And so once I have this family of operators, I can follow exactly the same principle, namely finding a representation where every layer I'm just going to learn a polynomial, or in that case, a linear combination of these outputs, right? And the parameters of the model are, how the weights, or like the coefficient of this linear combination at every stage. Okay, so this is what we call, together with my colleagues Michael Bornstein, Taco Cohen, and Peter Berlikovich, what we call this geometric deep learning blueprint, right? Because it's a blueprint that you can use in different domains, in the grid, you can use it in the graph, you can use it in the manifold, etc., etc., etc. Okay. Of course, the story this is just like the like the beginning of the story. There's many questions that are interesting from a mathematical perspective. For example, how do you parameterize this family of operators, right? I mean, what is the trade-off here? The trade-off again is this approximation versus stability, right? And some of the questions I told you about approximation, when we have symmetries, this question of approximation becomes a little bit more subtle, right? And so there's a lot of very interesting work that tries to understand very well the nature of this trade-off. All right, so just to as a takeaway of this picture of geometric deep learning, is really like it gives you like a framework, a geometrical framework, to think mathematically about a very large family of neural network architectures, right? That depend on in which domain they are defined. You have a natural keyword that maybe you have heard about, like these GNNs, deep set, the transformer, CNNs, RNNs, etc. All these architectures, they can be naturally fit into this way of thinking, into this blueprint. Okay, by just specifying the domain and the associated symmetry. I really want to emphasize, right, that this is really just a way to maybe formalize the problem and to define it mathematically, but there's still like a bunch of very, very important open questions, right? So we still don't have a good analysis of the resulting functional spaces, right? Like what is the role of the depth? That's not something that is totally answered by these architectures. Is there a question? Okay. Okay, very good. So now that we have seen a little bit about how can we use geometry to define hypothesis spaces, and we have seen the role of the multi-scale role and the role of invariances in controlling the approximation error, let me just spend a few minutes talking about the optimization aspects. Okay, so we have seen how this data structure is important to define these good approximation properties, right? So what about the optimization? And so I'm going to spend a few minutes introducing some of the challenges, the mathematical challenges that arise in this area. So to really the setup, just to refresh a little bit the notation, that we have some Briggs functional, some kind of error, notion of error. Sorry, I am hearing some background noise. No? Okay. All right, so we have some error, notion of error, that you can think that is a convex functional in the space of functions, right? It's a convex functional in my hypothesis space. And so this seems like from the optimization perspective, something a little bit inoffensive, harmless. The problem is that these hypothesis spaces, they're all highly non-trivial, right? So the way I typically parameterize this space of hypothesis, I said, is through maybe a neural network, right? It's like a mapping that is nonlinear, that maps the parameters of my model to the function. And so if I express these laws in terms of the parameters, now I basically break all the convex structure, right? So now I'm in a non-convex problem that really has probably bad properties, right? So there's some work from our group and also by the group of Ohad Shamir that really tells you that these optimization landscapes that arise from training neural networks, they have a bad landscape, right? So if I think about just following the gradient descent on this landscape, things might go wrong. So what is the state of affairs, right? Even if I have a very simple neural network architecture, for example, like the shallow one that I described before, what kind of guarantees we can obtain? So you might have seen, if you have been following the literature in this area, there's a recent that emerged a few years ago, like 3 years ago now, that considers this notion of overparametrization. So what is this overparametrization? It's really like the concept is that, okay, I might have this very complicated non-convex problem. What happens if I think about the problem as the width of this network grows? Does the problem become simpler, or does the problem become more and more complex? And so if I think about, again, in the shallow case, I can think about my function, again, as an average of rich functions. Okay, and so there's an important and interesting thing that one can do is that if I think about the function parameterized in this form, every one of these neurons has its own set of parameters. So I can think about each one of these neurons as a particle, right, in some domain that is parameterized by, in that case, like some finite dimensional domain. So the system is parameterized by these particles. So I can if the number of particles increases, I can take the route that the traditional route in statistical mechanics, that is to change the perspective, right? Instead of describing the system in terms of the position of the particles, I can try to describe it in terms of the density of the particles, right? That's what's called the Eulerian perspective. Okay, so if I introduce this empirical measure, then I can re-express the function, right? So this is like an equality, there's no error here. I can re-express it as an expectation over my empirical measure. But now observe that the dependency between my parameter, right, if I describe the system with this mu, now the function depends linearly on the measure. So it means that now I can get back again this convex structure, right? Because if my loss is convex with respect to f, it's also going to be convex with respect to mu. Okay? Of course, things are a bit more complicated because now I need to understand how to optimize things, how to move, right? How to optimize things in the space of measures, which really has a geometry that is really different from the Euclidean geometry, right? In that case, the relevant metric is what's called the Watt-system metric. And I believe there's a mini symposia this week that is, I think, going to cover some of the connections between machine learning and optimal transport, right? Which is something that is at the core of this technique here. And so the point is that as the width of the network increases, goes to infinity, then we can really inherit basically this global convergence guarantees that we have in what we call the mean field limit, right? When I replace this empirical measure by its associated limit, right? By the limit in which I basically just use the law of the parameters that I use to initialize. So basically I can go to the limit and obtain very nice and beautiful global convergent results, right? That really need to deal in a way that is non-trivial with this Wasserstein measure, right? Wasserstein gradient flows. And so I can basically say, give a qualitative answer that, okay, this optimization problem is very complicated, right? It's non-convex, as I said before, but as you have more and more and more neurons, you know, in a sense, in the average case, the problem becomes tractable, just because I can rely on this like global convergence from the mean field limit. Of course, there's a problem, right? Is that if you want to make this thing quantitative, how large should you make the number of neurons for this result to be useful? And in fact, we are hit again by the course of dimensionality, right? That if I have a measure, initial measure that brings me this global convergence, right? Like that, where if I run my gradient flow from these dynamics, from this measure, I can reach a global minimizer. If I want to recover this guarantee with a finite neural network, basically what I need to do is I need to grid the space. I need to put, I need to cover my parameter space with basically neurons that are gridding the space, right? And because the space is again high dimensional, I'm again, in a sense, I'm toast, right? Because if I want to make this error small, I need to have a number of neurons that is exponential in the dimension. So is there some, is it like a failure of the technique, right? Is it because we are not finding the right tool, or is it because there's a fundamental hardness, right? Is it a problem that is inherently hard, or is it just a limitation of the proof technique? And so that's the question that we were studying with, again, my PhD student Minjai Song and postdoc Ilya Zadik, who is now at MIT. And so in fact, the answer that we provide is actually pretty negative, in the sense that the problem, in fact, is hard, is inherently hard, in the sense that if I can construct hypothesis spaces, like target functions that are really just obtained by a single neuron, right? So a single neuron, even learning this function, we can prove that is essentially computationally hard, right? And let me just explain a little bit what this is about. So essentially learning this function amounts to being able to solve the following classification problem, right? So I'm gonna just, I don't know if you can see this video here moving, right? It's a video that is moving. And so somehow there is these 2 point clouds, they look very close to each other, but they're not the same, right? If you look at this thing from the right angle, you can discover that there's kind of a hidden periodic structure, right, in this problem. And this is the periodic structure that you can see, of course, by the way I planted this function. So in fact, we can show that solving this problem easily reduces from solving a complicated problem in lattices, right, which is called the shortest vector problem. And this shortest vector problem, like the hardness of this problem, is the foundation of modern cryptography, like a post-quantum cryptography, right? So basically, the reason why we can have these crypto systems, even in the post-quantum world, is because this problem is fundamentally hard, right? So it's not NP hard, but it's what we believe to be cryptographically hard. So basically, if you were able to solve this problem, to learn this function, you would be essentially breaking modern cryptography, right? So this really makes you very skeptical that there's any algorithm that can work that can solve this problem in polynomial time. Okay, and so of course, in general, things might not be so bad, right? Because here I'm just constructed this very specific function, right? That has this hidden dimension that oscillates, right? So if you really want to recover positive results, right? Like which functions we can learn that use a number of resources that is polynomial in dimension, right? That is doesn't scale exponentially in dimension. We need to really exploit the smoothness of the activation function. Right, and today, of course, I don't have time to delve into this line of work, but I just wanted to highlight here that this is a very beautiful area that is really at the crossroads of many techniques, right? So there's techniques, as I said before, as I just mentioned, from actually theoretical computer science, for example, studying algorithms on lattices, but there's also actually work that uses a little bit more like high-dimensional probability, right? This idea that maybe random structures in high dimensions, they're not only a source of like headache, right, like this course of dimensionality, but if I look at them from the probability angle, I have even like what's called like the blessing of dimensionality, right, like the ability, like finding this very, very adversarial oscillating structure in high dimension. Maybe that's not something I'm going to find very often, right? So I can rely on the fact that on average, I might have problems that are easier. And so the smoothness of the activation function is something that has been used throughout the years, even like recent works that I'm doing alongside my colleague Jonathan Nileswaite, where we really exploit this thing. And the really like the picture that you should have is that when I have an activation function that is smooth, I can basically, instead of trying to optimize the original optimization landscape that you have here on the left, I can afford to essentially smooth the landscape, right? So I have algorithms, and I can run algorithms efficiently in high dimensions that instead of using this landscape, they use the landscape that is here on the right, okay? And so, of course, if my activation function is like a cosine, right, and is very oscillating, as I smooth, I lose the information, right? There's nothing I can use in this picture on the right-hand side. But if the activation function is sufficiently smooth, yes?
5 minutes.
Yeah, thank you. Then I can use that. Okay, so the takeaway here is that if I want to overcome distribution-specific hardness, I need to leverage this assumption, the smoothness on the target function. All right, so that's good because I have 5 minutes left. So I'm just going to end with the 5 minutes by just trying to motivate a couple of applications that these methods have in what we call the scientific machine learning, which is kind of like a nascent discipline that is really at the interface of another area of mathematics, like numerical analysis and scientific computing and machine learning. So just to motivate, just like a couple of snippets, right, very quick. So if I want to, in many areas in computational science, I have to deal with phenomena that is random, right, like a random phenomena that is modeled as random phenomena, but where the randomness is inherently non-Gaussian, right? And just give you 3 simple examples. If I study turbulence, for example, if I want to do Clivant models, I need to deal with kind of turbulent phenomena like Navier-Stokes, like people who study glasses, like Ising model is another example of a highly non-trivial, non-Gaussian model. Or if I want to do like cosmology, right, like the effect of gravitation creates this kind of like non-Gaussian phenomenon. And so a very natural model, like to go beyond this Gaussian assumption, is to use like models for this these density functions that are non-Gaussian, but are still like have like sufficient sufficient structure so I can study them. And a natural class is like these Gibbs measures where the sufficient statistics are given by certain representation. And so if I use, just to convince you that this is really not a Gaussian model, if I use as a sufficient statistic just a covariance, right? I'm using a Gaussian representation. As you can see that the Gaussian representation doesn't really capture the physics at all, right? But if I use instead the scattering coefficients that I told you before, right? I have a representation that is still like very easy to estimate because I have a number of parameters here that is very small with respect to the dimension, right? It's like just logarithmic with respect to the dimension. And you can see that the models that I learned here, even though they are maybe not perfect, they're really nailing, they're capturing like the essence of the problem. Like the physics are totally, like the properties, the statistical properties of these processes are very well captured by these scattering Gibbs models. Okay?
Pues a mí no me parece.
Excuse me? Okay, I don't know if that was for me. And so just to show you that another area where this thing has been used is to estimate parameters in weak lengths in cosmology, right? That's something in collaboration with Brice Menard and his students. We use the scattering transform to actually improve the estimation of certain cosmological parameters using actually weak lengths, right? And so the takeaway here is that this like structured neural network, like these structured convolutional networks given by scattering coefficients, they are really like a good trade-off, right? A good tool in many areas of computational science where you don't need a lot of data to set them up. And the last thing I wanted to do, and this is really like the last item, is that there's another opportunity that is in front of us that is that leverages these tools that we are developing on machine learning. That is to use machine learning but without data, right? This seems like a contradiction, right? Like machine learning is typically associated with absorbing a lot of data and then learning from this. But in fact, there's an interesting alternative that is just to use the tools like the functional spaces that I described to solve, let's say, traditional problems in scientific computing. And here I'm just gonna end up with a very simple application that is just essentially a very classic problem in numeric analysis that is just to solve numerically a PDE, which is, I guess, maybe like the bread and butter of applied mathematics, at least like a big chunk of it. Okay? And so as you know, numerically solving a PDE is also about approximating a function, right? And as soon as the PD is defined over high dimensions, this problem is actually, again, going to be suffering from the curse of dimensionality. So the sort of model that we are describing, that we are developing with my colleagues Benjamin Herstoffer and Eric van den Eyden from Courant, is the ability of neural networks to solve numerically integrate PDs. And here, of course, I'm showing you a very simple toy problem, that is the Burger's equation, which is, of course, in 1D. But this really hopefully shows that there's some interest in actually going beyond these grid methods, for example, the finite element method. Right? So these neural networks, they're able to actually approximate functions without relying on the grid. And this makes them much more attractive to approximate problems in high dimensions. And so just to wrap up, what I try to describe today is just a problem, like a very general problem that is really about learning functions in high dimensions. But these functions in high dimensions, they are living in the physical world. And so the physical world is bringing us a battery of tools that range from signal processing, harmonic analysis, etc., that I think open up a very lot of interesting mathematical questions. And of course, there's both prospect and challenge, right? So I think there's a lot of potential for these applications to change completely like the way we do computational science. But of course, there's a lot of work to be done, right? Like especially from the mathematical side, on really trying to understand a bit better and provide a bit more guarantees for these approximations. So with that, thank you very much. And these are also like acknowledging all the collaborators that have been co-responsible for this work. Thank you very much.